This biomedical instrumentation lecture covers temperature transducers. Temperature is one of the most important variables to measure from the body to determine its state, and it's highly informative to physicians. So some examples are shock, in which blood pressure goes down, which leads to low peripheral blood flow, which leads to a drop in temperature. In infection, you can get temperature increases due to fever. With anesthesia, temperature tends to go down. Infant incubation is an important scenario in which to monitor temperature. In arthritis, you get inflamed joints. And you get higher temperatures then in those joints, in those inflamed joints. It also can change as a result of ovulation. In this lecture, we are going to cover several different kinds of temperature transducers. The first is going to be thermal expansion. Then thermistors. Thermocouples. Semiconductors. And in the next lecture, we're going to cover thermography. So these are the guys that we're going to cover in this lecture. Whatever temperature transducer we use, heat must flow into the sensor from the body. And when the sensor comes into contact with the body, its temperature and its output will transition from whatever state it started at to the body's state. And until thermal equilibrium is reached, there will be a flow of heat from the body to the sensor. The heat flow will stop when when the temperature of the sensor is equal to the temperature of the body. So the temperature of the transducer will start at its own initial baseline. We'll say that that's T sensor of time 0, and this is the time axis. And it will transition up to T body with a decaying exponential. So this function is 1 minus e to the minus t over tau, where this tau here is a time constant. That depends on factors such as the size, mass, and the material that the transducer is made out of. Large sensors naturally require more time to reach the body's temperature, so they have a higher tau. So the first class of transducers we'll talk about is just mercury or alcohol thermometers that are based on the expansion of these materials with changes in temperature. And these can be depicted graphically just as a reservoir with a tube coming out of it with different multiple gradations across the length of the tube. So here's a large reservoir. And here we have a calibrated tube. I say calibrated, and when I say calibrated, I mean that somebody has already figured out what the gradations along the length of the tube mean in terms of temperature. And we'll say that the tube has cross-sectional area A. A Okay, so why would we use a large reservoir and a narrow tube? Well, if we call delta V the change in volume for a given temperature, we'll say that that's equal to A times delta L. We have this relationship must hold, that the change in volume for a given change in temperature must equal the cross-sectional area times the change in the length along which the liquid has moved. So since delta V is fixed for a given change in temperature, as the cross-sectional area decreases, the length along which the liquid will move for a given change in temperature increases. And this is a form of mechanical amplification. Now the range of these thermometers is limited fundamentally by the length of the tube and also by the boiling or freezing point of the liquid. The resolution is limited by the reader's visual acuity and also the spacing of the gradations. That is, the marks along the length of the tube. The precision is perfect, and the accuracy will be affected by pressure. Since the delta V will be a function of pressure and temperature. The time response of a mercury or alcohol thermometer depends on the reservoir volume, since for a larger volume it will take more time to change temperature. This will be a trade-off with resolution, since if we have more liquid, we can make a longer tube we can make a longer, narrower tube coming out of it and get better resolution. Overall, the time constant is proportional to the volume of the liquid in the reservoir. The main two challenges with mercury and alcohol thermometers are that they are fragile and slow and big, and they have no electric output. The second class of temperature transducers is thermistors. These are chunks of semiconductors that have a high negative temperature coefficient, and they react opposite to metals with changes in temperature. However, they have a much larger, in terms of amplitude, temperature coefficient than pure metals, and as the temperature goes up, the resistance goes down, as you may recall from the Arduino lab. Thermistors have a high sensitivity, though, because of their large temperature coefficient. They can vary 3 to 5. They can change on the order of 3 to 5% of their nominal resistance per degree C, and their temperature dependence is given by the following equation. It's RT naught. This is in ohms, a baseline resistance, times e to the beta 1 over t, the actual temperature, minus 1 over t naught, the temperature at which RT naught was measured. Beta here is called a temperature coefficient, and it's usually on the order of 3,000 to 4,000 Kelvin. Usually a thermistor is placed in a bridge circuit to convert the change in resistance to a change in voltage. Thermistors have a few nice strengths. One is that they're very cheap. They are linear over small ranges, pretty linear over small ranges. And they are very rugged. You can stick them on the end of a device that you stick in the body, like they are often used on the ends of ablation needles that are inserted into the body. The third class of temperature transducer is thermocouples. And these devices are based on the Seebeck effect, which describes that due to the migration of charge carriers, any conductor, like a length of wire, in a thermal gradient will generate a voltage along its length. So here's a typical setup of a thermocouple. You'll have these two output points across which you'll measure some voltage V out. You'll have some lead wire, which will be made from some unrelated metal to what the thermocouple is made out of. You'll have it connected to the two wires that make up the thermocouple in what's called a cold junction. Then you'll have the thermocouple here, and I'll label these in just a second. The two wires of the thermocouple here. So here's your cold junction. And this is at some known reference temperature. Then you'll have two metals, metal A and metal B, that make up the actual thermocouple. And they will be inserted, they will be connected here at this point that is at temperature T. And we can draw an equivalent circuit for this, which is that we have basically two opposed batteries. There's the temperature at point T. Now, the Seebeck effect again says that due to the migration of charge carriers with when you place a wire in a thermal gradient, you get a voltage along the length of the wire. But there's another thing you need to know, which is that the amount of voltage depends on the type of wire that you use, the type of metal that the wire is made out of. So metal A here is going to create a different voltage along its length than metal B, even though they have the same temperature gradient along their lengths. And so that means that these two batteries here will have different amplitudes. And so if you use the same metal on both sides, you'd have the same batteries here and you get 0 voltage at the output. Because you use two different metals, you get two different voltages here, and you get a voltage difference, a non-zero voltage difference. And that non-zero voltage difference is equal to this constant alpha times the temperature that of the junction minus the temperature at the reference point. Alpha here is called the metal pair sensitivity, and it depends on the two metals that you use for the thermocouple. The two most common metal pairs are iron and constantan, and copper and constantan. Constantan is a copper-nickel alloy. So overall, these have, you can see that the units of alpha are microvolts per degree C, so that's pretty low sensitivity. But because these are not resistive devices, they have a low noise and also low output impedance. So it's easy to amplify them to get very high sensitivity. There are a couple challenges with using thermocouples. The first is that it requires the reference temperature to be kept constant. And again, as I said, you have low sensitivity without amplification. But they have many strengths. One is that they have a very high temperature range, higher than any of the other devices we're talking about. You can make thermocouples that will work at minus 270 to 2500 degrees Celsius. It's an enormous range. You can increase the sensitivity by putting N junctions in series, which gives you a thermocouple. It gives you a thermopile. And it increases your sensitivity by a factor of N. Caveat, of course, is that you're going to have a slower response time. So here's what that would look like. You'd have your leads coming out of the device, you'd have your common cold junction, and then you'd have multiple thermocouples in series across which you'd get a larger voltage. Thermocouples overall are best for small changes in temperature due to their high accuracy. They can be made very small, so intracellular recordings are possible. They have very fast response time due to their small tau if you don't use a thermopile. They're easy to build and they can be stable over the long term. The fourth class of temperature transducers are semiconductors, and we're going to talk about two subtypes in this category, the first of which is the PN junction diode thermometer. So we haven't really talked much about diodes in class yet, so I wanted to do first a brief introduction to PN junction diodes. So here's an electrical schematic of a PN junction diode. It has this upside down triangle with a line across the end, and it has two ends, the positive end and the minus end. The positive end is called the anode, and the negative end is called the cathode. And these were the first semiconductors, first semiconductor devices. And they're made by bringing two different types of doped semiconductor material together, sort of blowing up the schematic here. You bring together a p-type semiconductor and an n-type semiconductor. And the p-type semiconductor is doped with impurities that steal electrons from the silicon's valence band. Conversely, n-type semiconductor is doped with impurities that add electrons to silicon's valence band. So add versus steal. And when we bring these two materials together, we get in the middle here what's called a depletion region, which is like an insulator region with an electrical field across it, a built-in electric field across it. And there are no charge carriers. So what you have to do, the reason why a diode acts like a voltage-controlled switch is that you have to apply a voltage across it that cancels the electric field in the depletion region. So you have to apply a voltage that cancels this electric field across the depletion region such that you can start to get charge carriers that will cross it. And overall then, the curve that we get from this looks like this. This is the IV curve. So once you've applied enough voltage across it to cancel that electric field, current starts to flow. Okay, and this point here at which it starts to turn on is called the turn-on voltage. In this turn-on voltage, Vt is a function of temperature, so that the overall diode current that we get is equal to this, what's called saturation current, times e to the lambda V sub d, which is the diode or voltage across the diode, divided by this turn-on voltage V sub t minus 1. So again, this I sub s is the saturation current, And this V sub D is the voltage that we apply across the diode. Lambda here is a manufacturing constant. And V sub T is equal to K, Boltzmann's constant, times the temperature in Kelvin divided by Q, the charge of an electron. So I'll again define here K is Boltzmann's constant. T is the temperature in Kelvin. And Q is the charge of an electron. As the diode's junction heats up, more electrons become mobile, so less voltage is required for current to flow. And that's what makes this a good temperature transducer. And this means that the diode's IV curve shifts to the left for increasing temperature. So that would look like this. We have the voltage across the diode. We have the current through the diode. This is about 0.7 volts for a PN junction diode. If we have one temperature T1, and then we change the temperature, specifically here we're increasing the temperature. So this is at temperature T2. So then T2 here is greater than T1. And so what we would do here is in a circuit, we would place a constant voltage across the diode somewhere near its turn-on voltage. So that we can measure VD, the voltage across it. We'd have some fixed resistance R to limit the current going through it. And we'd have then the diode current I sub D there. Here's V sub S. So V sub D, the diode voltage, is equal to V sub S, the fixed source voltage, minus I sub D times the fixed resistance R. And if we make the substitution here for the diode current equation on the previous slide, two slides ago, we would get V sub S minus R times I sub S times e to the lambda V sub D divided by V sub T minus 1. And because V sub T is equal to KT over Q, we can solve for the temperature T if we know V sub D by measuring it in this way. So some advantages, some strengths to PN junction diodes are that they are sensitive and very tiny, and while they're nonlinear, they are approximately linear over a small range. So the second type of semiconductor temperature transducer is the Zener diode thermometers. So here's a Zener symbol. We saw this in another lecture recently. It looks kind of like a ninja weapon here, and it acts like two anti-parallel diodes. So we can, for the purpose of analyzing its function in a circuit, we can treat it as two anti-parallel diodes. Which gives us a somewhat symmetric IV curve. We get turn-on voltages for both positive and negative turn-on voltages. And what we're going to do here is we're going to exploit the fact that the negative turn-on voltage is very dependent on temperature. So here's how we would use it in a circuit. We would, again, like in the p-n junction diode case, have a fixed source voltage, a fixed resistor, and then a Zener diode. And we'd measure the voltage across the Zener diode. The Zener diode would be upside down so that we're looking at its negative turn-on voltage. And it turns out it's quite linear with temperature. So V out here is 10 millivolts, approximately 10 millivolts per Kelvin, times the temperature in Kelvin. So that's pretty darn sensitive. And what you get here is about 2.98 volts at 25 degrees C, which is room temperature. So that means that for two different temperatures, its IV curve is going to look something like this. You have your turn-on voltages here. So this is I and V. So let's say that this is temperature 1. If you then heat up the Zener diode, you'll get the temperature moving to the left. And it's not going to change quite as much on the positive side. So this is T2. And here, T2 is greater than T1. Zener diodes have a couple challenges in that they have a high time constant tau, which is about 3 minutes in air, and about 3 seconds in oil. It also has a relatively limited range, but body temperatures are okay. Among its strengths are its accuracy. It's easy to use, and it's very linear over this range. So that's it. In this lecture, we covered temperature transducers and talked about 4 specific classes: thermal expansion, thermistors, thermocouples, and semiconductors. Next time, we'll talk about thermography.